Good afternoon. Oh, what a great crowd. Thank you so much for being with us this afternoon. My name is Evelyn Hammonds. I am Dean of Harvard College and the Barbara Gutman Rosencrantz Professor of the History of Science and of African and African American Studies. It's actually not the longest title at Harvard. I am also a proud museum overseer and a member of the Women in Science Committee. And I'm going to be your host for this afternoon. We have a wonderful program, and it is my pleasure to welcome you to the 15th anniversary celebration of the Women in Science Luncheon Series. Now, I was not involved with the museum in 1997 at this series' inception, but I can tell you in 1997, I was an inveterate attendee at all kinds of museum events and their exhibits. So I feel like my relationship with the museum goes all the way back to the very first time I came to Boston in 1976, because I grew up in Atlanta and there wasn't a museum of science. And I arrived here and they said, there's a museum of science. And I said, I have to go. And I've been coming ever since. And of course, as you know, the museum has changed and grown and is an absolutely wonderful and important institution in our community. So I think many of you also have been here for quite a while. So we welcome you, and we welcome those who, this is one of your first times enjoying our, participating in our luncheon. You have so much to be proud of. And I want to say, in terms of this 15th anniversary celebration, we have so much to celebrate. So we're going to begin, and it's my pleasure to introduce Jessie Deshpande, who is co-chair of the museum's Women in Science Committee. I'm going to talk a little bit slower. She's chair of our Women in Science Committee, and she is coming to the podium to offer a few remarks.
Good afternoon. I'm Jessie Deshpande, co-chair of the 2012 Women in Science Committee. I co-chair this committee with Susan Whitehead. Susan, can you please stand up? Yeah, thank you, Susan. It is indeed our great pleasure to welcome each of you today for this special occasion, our 15th anniversary celebration. As Evelyn mentioned, our Women in Science Luncheon Series began in 1997 as a unique forum for distinguished women scientists and engineers to share their groundbreaking research with almost all women audience. We welcome the brave men who join us. We were one of the first groups locally to undertake such an effort and a commitment to gender equity. We are so proud of the very distinguished speakers we have attracted over 15 years. The full list is in your afternoon program. We are also proud of the way our series has grown into such a strong mentor program for young women scientists and engineers to build lasting connections. At this point, I would like to recognize members of the Women in Science Committee who worked behind the scenes to make this all happen, many of whom have been with us since the beginning. Could I please request all the Women in Science Committee members to rise, please? Yeah, thank you. I would also like to acknowledge our longtime supporters, Priscilla and Richard Hunt, who have generously sponsored today's event. Thank you. Thank you. They have supported the luncheon series for years through the Roy A. Hunt Foundation. We are so grateful for your support and your commitment and to educational opportunities for women and girls. And thank you all for coming today. I hope each one of you will take a moment to introduce yourself around the table and share your stories and your fond memories of the museum. For this 15th anniversary occasion, we are very proud to have with us today a very special leader, Dr. Yanis Mialis, the museum's president and director. Yanis himself, a longtime advocate of gender equity, is a 2012 Science Club for Girls Catalyst Award honoree. Under Yanis' leadership, the museum continues to support our committee's efforts wholeheartedly. Please join me in welcoming Yanis.
Thank you, Jessie, for your kind introduction and for all the wonderful things you do, both for the committee and for the museum. First, I would like to congratulate the Women in Science Committee for its 15th anniversary. And both of my daughters, Marina and Katrina, are engineers, both mechanical engineers. And I deserve full credit for that simply by not telling them to become engineers. Because I know I would have had 2 drama majors if I did say that. And the older one, Marina, graduated last year from Tufts, and she got a wonderful job at Pegasystems, just around here, and she's off my payroll, which is very nice. The other one is heavily into my payroll. She's still a sophomore at Tufts, and also a mechanical engineer. Access is one of the funding priorities for the campaign for the Museum of Science and for this committee, the Women in Science Committee, and which, along with Dr. and Mrs. Hunt, have been making accessibility to networking and role models a reality at the Museum for Young Women for 15 years via this Luncheon series. And thank you so much for your efforts. Now, some of you are new to the museum, so I just want to take a couple of minutes to tell you what's happening here at the museum now. We formed a new council, the Technology Leadership Council, and actually 2 members of this group here, Will Yord and Helen Greiner, are 2 of the leaders of this committee. And the Technology Leadership Council will advise us on how to proceed in including more engineering and technology exhibits and programs in the Museum of Science. One of the activities of the committee is to advise us on the creation of a new exhibit that we're developing, which is called Science of Pixar, Pixar House of Animation. This will be a traveling exhibit, and it will be our very first exhibit on computer science. So we're slowly moving in the computer science area, and we want to do with computer science what we have done with engineering, including computer science both in our offerings to the museum, in traveling exhibits, and also in educational programs for schools and children. The Pixar will hope to be a blockbuster exhibit, and it's pretty much in the same spirit, developing the same spirit as the Star Wars exhibit. Our Star Wars exhibit was our first engineering exhibit, and Pixar will be our first computer science exhibit. But our biggest news is the Hall of Human Life. If you walk to the museum second floor, you'll see the whole area is blocked because we're actually building the Hall of Human Life now. It's going to be the most spectacular exhibit on human biology, nutrition, and evolution in the world. And we're hoping to open it, actually we will open it, we're always on time, on November 2013. We also hired a new leader for the Hall of Human Life, Elizabeth Kong. Elizabeth comes to the museum with a strong background in the life sciences. She has a PhD from Tufts University, a very strong background in oncology research, and a deep interest in sharing bioscience education with museum visitors. And we're very fortunate to have her join our team. And Elizabeth is here today. Would you stand, Elizabeth? Welcome. So once again, I would like to congratulate the committee for its 15th anniversary. Thank you all for coming, and please enjoy your lunch, and we'll continue with the program after we eat. Thank you.
I hate to take you away from this wonderful lunch and what I assume to be really many wonderful conversations, but now it's time for us to resume our program. It's now my pleasure to introduce Susan Whitehead, who's Jasree's fellow co-chair of the museum's Women in Science Committee, for a few remarks.
Thanks, Evelyn. So it's great to be here with you today. Can you hear me? Okay, great. Celebrating the 15th anniversary with you. It's really an honor. I just want to start out by saying to be part of the Women in Science Committee, to have had the opportunity to co-chair it, and I just want to say out loud that I have particularly enjoyed co-chairing it with you, Jessie. I think we've had a good time. So this is a very invigorated and passionate group, this committee. And in the last 2 months, I just want to very briefly tell you that we launched 2 initiatives in celebration of the 15th anniversary, and I'd like to share them with you. The first initiative was something that Jessie conceived, and the idea was to launch an essay contest for high school girls who were interested in science and engineering to talk about the role a mentor has played in their scientific or engineering pursuits. We were really delighted. We got entrants from 7 different states in the US, and our jury, which was comprised of professional women who were on the Women in Science Committee, as well as education staff at the museum, chose 5 of those entrants to win the prize. And they covered, these young women were truly extraordinary, covered everything from someone who had participated in a NASA program to another young woman who had advised the mayor of one of our western cities, to other people who had been interns in research. And you can see some excerpts from their essays in your booklets. I think, is Katie Kester here with us today? Hi, Katie Kester. Could you just stand for a minute? And the reason why I'm naming Katie is she was one of our 5 winners of this essay contest. It's great to have you with us. Thank you, Katie. Congratulations, and we look forward to watching what routes you take through your life in science and engineering. So the second initiative, which we decided to launch out of the committee, was also in honor of the 15th anniversary, because we were really proud of these 15 years and what Women in Science has done and can do going forward. So we really brainstormed about what we might do to honor this occasion, and we decided to launch something that we are calling the Women in Science Endowed Innovation Fund. And we have started to refer to it locally as the WISE Fund, Women in Science Endowment. We launched this for a couple of really very straightforward reasons. We wanted to support the museum. We wanted to support women and girls who are particularly interested in science and engineering. And we wanted to support innovation. And we thought this was a great co-branding. And we thought that it was a splendid convergence. So I'm really delighted to tell you, and a little surprised but delighted, to tell you that with very early fundraising, just from a number of committee members from Women in Science, we've raised almost $240,000. So we're thrilled. And obviously, you're welcome to join us if you would like. But I also wanted to just tell you very briefly, because I don't want to interfere with time for our panel, but I want to tell you what we chose as the first focus of the fund and where we would distribute those funds. So what we have chosen to support is the museum's Design Challenge Maker Spaces. And this is a program of the museum that was launched in 2003. And I think some of this is being shown on the screen. And I want to just tell you specifically why we chose to support these programs. They're at the forefront of innovation. The seed funds for this program will be very important to help them to firmly establish the Museum of Science as one of the primary leaders in this design educational concept. This is also a very popular exhibition and space, worker space, maker space at the museum. It attracts both boys and girls. And it's also being led by somebody who's really dynamic, Lydia Beal. And Lydia, are you here with us today? I can't see. Oh, hi, Lydia. Could you just stand for a minute, too? Thank you. And Lydia's leadership has really been spectacular of this initiative at the museum, and we wanted to support something that was tried and true with really great leadership. She's dynamic, creative, and one thing that particularly appealed to us is she's also very interested in conducting research to look at both the barriers and opportunities specifically around these design challenges to getting girls to use these maker spaces. So this program, again, offered a really great convergence for us. It was proven excellence, innovation, leadership, and research. So simply said, we are delighted. We hope you like these ideas. And if you'd like any more information about either of these two initiatives, either the essay contest, which we're just deciding whether that will be embedded permanently or not, or the WISE Fund for Innovation, please fill out the form in your program so that we would know how to get in touch with you. And it's also something that we'd love you to fill out if you're interested in any more information about anything going on at the Museum of Science. So thanks for joining us today, and enjoy the journey. Thanks.
Thank you, Susan. Those are some really, really exciting initiatives, and I hope many of you will take an opportunity to participate in them. It's a very important and inspiring time here in the museum, and I really want to emphasize how important this work of the Women in Science Committee is, and particularly in celebrating the spirit of mentorship and the lifelong pursuit of learning. There are no famous, wonderful, incredible, creative scientists who did it without mentors. Mentors are key to the production of scientific knowledge and the transmission of that knowledge over generations. So it's very important that we support the kind of efforts that make sure that young women who are interested in science have the kind of mentorship and inspirational leadership that helps them follow their dreams. Before I introduce our first special guest, I want to do a little bit of housekeeping and let you know how the program will go. Our guest speakers will make brief presentations this afternoon, and then we'll have a very robust, I hope, conversation with all of you. We know you want to have time to ask questions of our trailblazers. If you have a question, please note that there are some cards and pencils next to the dessert on your tables, and we ask you to write your questions on those cards, and the staff will pick them up, and we will use them to answer put questions to our presenters. Also, their full bios are available on your afternoon programs, and so in the interest of time, I will just give them brief introductions. So our first guest is Dr. Mary C. Boyce, the first woman department head of mechanical engineering and the Ford Professor of Engineering at MIT. Dr. Boyce teaches and conducts research in the areas of mechanics and materials. She is a member of the National Academy of Engineering, and she has mentored 36 Master of Science thesis students and 25 PhD students. Dr. Boyce.
So first, let me thank you all for coming, and it's really a pleasure to see so many women, maybe a couple of men, really committed to women in science and engineering, and I think this is really a key to our future in advancing a lot of the world's challenges. So what I'm going to talk about first is a little bit a snapshot of some of the research I do with my students at MIT. I think actually a lot of that is key to mentoring that next generation of leaders. It's really having problems that we're really passionate about and inspired to find solutions to, and this really attracts people to the field. And then I'll try to close off with a little bit of a map of where this impact lies in terms of people. So the title of my talk is Motivated by Challenges, Inspired by Nature, and How Mechanics Shapes Our World. So my background really is mechanics and materials, and looking at how the structure of something and the combination of the materials in it gives rise to performance, to how you can actually engineer and use materials and structures in engineering solutions. We're motivated by challenges. We look at whether it's from safety and security to lightweight structures for automotive and aerospace applications to new types of materials for membranes for cleaning water. So many, many different kinds of challenges motivate why we work on our engineering problems. And in my work, we are also very much inspired by how nature has found a solution to many of these challenges. So we try to put those pieces together. And what we see is underlying many things is the basic mechanics really shapes many solutions. So where's the clicker? So I'm going to just give a snapshot of a few examples. And for those who are really interested, I do have some hands-on. I'm an engineer. I love to have something to show, some show and tell, so you can come up afterward and take a look at something. So one of the things we see in nature is, and it's a problem that we see in many man-made engineered structures and materials, is how do we put two different kinds of materials together and still achieve an optimal functionality? And one of the ways nature does that is through what are called suture joints. So most of you are going to be familiar with that. It's because of our skull. It's actually lots of rigid pieces that are actually bonded together with these wavy suture joints. And that's what's shown here as this wavy suture joint that binds and connects different parts of your skull. We also see this in fish, where fish are trying to have a protective armor but yet have flexibility. So they also need it to be able to have some compliance so that it can accomplish its other criteria. So one of the other interesting things we see here is if you look at some suture joints, not only are they wavy, okay, but they will have a wave on top of a wave. We call that a hierarchical structure. So one structure on top of another. So these sorts of things open up very interesting questions. So for example, we wonder, why does nature, whoops, the red light's not working. Why does nature in a single wave suture have very triangular geometry? Right? Why does nature choose to have a hierarchical geometry in some cases? So we look at the mechanics of why does nature choose to put structures together in this way. So we call this a single wave suture joint. And now here's a hierarchical structure where you have really a self-similar wave on another wave. Okay? People call these fractals as well. We use equations in what we do. I'm not going to go through those. But those who are interested, I'm happy to do so. But what we find after we really analyze, do the real engineering of this, is we find really fascinating solutions. We find that a structure that is triangular in nature, which normally we would think that's going to give some really terrible mechanical features, that it's going to give what we'd call stress concentrations, which would lead to failure. And instead what we find is a triangular structure is a constant stress structure. This is a structure which is actually optimized. Nature has figured out that a triangular suture is actually mechanically the best kind of geometry out there. That's really surprising. Okay. We also find that nature will then go in and put different wavelengths in different parts of a structure. So have very high amplitude, tightly spaced triangles in some part of it, and widely spaced, low amplitude, triangles in another part. And this all actually comes out, and when you go back and look at the mechanical function, is absolutely tailored for what the property was needed at that location. So it's really amazing that nature can figure this out. Here is showing an active pelvic suture of a synalogous fish, the Polyptera synagalus. What happens here is that right here you have a very high amplitude suture joint, and it's because it has to actually support incredible loads for when it's fighting off its predator, which actually happens to be another Polyptera synagalus. So you actually learn a lot about evolutionary biology, which is not a path I thought I was going to be taking when I was a mechanical engineer, but this is something we're doing now. When we go and look at the suture of a skull, what you find is that in an infant, these suture joints are very flat. In an adult, they're very high amplitude waves. And it's when you're a baby, your skull has to grow. It needs to have a compliant bond. And when you're an adult, your skull is really there to protect you. And so your suture actually changes to accommodate your stage of life. We also find that these hierarchical structures, really amazing, is that nature has just a couple of materials at its hands. It has this organic, compliant material and the very stiff, inorganic, mineralized skeleton. And yet it creates properties that are the whole range of mechanical spectrum, different stiffnesses, different strengths, different toughnesses. And how it does that is by just changing the geometry. And so what nature does is that when it needed to be stiffer, oh great, thanks. When it needed to be stiffer, it would go in and replace the bonding adhesive with, it says, well, I don't have another bonding adhesive. I can't just go to the hardware store and buy a different glue, right? It's only got one kind of glue. So it will go in and create a hierarchical structure and put some of the skeleton material in there with it. And this is exactly why nature does these hierarchical structures, because it needed different properties later on. So these are really very fascinating things that we find nature does, and we can see exactly how many hierarchies are needed. We can use engineering to do this, and so we can actually use engineering to uncover the rules of nature and then map those now into lightweight structures for engineered purposes. I want to just go over one more quick example. And here, when we were looking at, because your research takes you in many different paths, and I think having that curious mind and wanting to just follow what you find. We were looking to see what other kind of suture joints were out there, and we found that there were other wavy joints out there, but instead of putting two stiff materials together, they were putting two soft materials together with a stiff, wavy bond. Right? And so we find this, and we find them in plants, we find them in the eyes of sea creatures, and we find them actually even in our arteries, where you have very compliant materials put together with stiff, wavy lines. And again, we find mechanics, not surprising given I'm a mechanics person, is the key to these structures. Again, we use equations, we use simulations, I'll skip through those, but what we're finding is really it's basically what we call a buckling phenomenon. So, every one of us has had some sort of structure which is long and thin. In nature, this buckling is then mitigated by the surrounding soft material to give you these wavy, different structures. So again, nature is using mechanics to actually create microstructures which then help it achieve its function. So these are the sorts of things that we've been looking at in my group, and then looking at using those to actually engineer new materials and new structures. So this is just showing that we can actually engineer the structure through very careful control of things like thicknesses, spacing, relative modulus of different materials. I won't bore you with those details, but it's exciting to some of us here. And these also then map on not just to lines and interfaces, but then putting these lines and interfaces into different geometries, and so that we can create really unusual types of topographies and also types of morphologies of structures. And these are structures that we see routinely in nature. So nature has figured out how to really use mechanics as a guiding principle to create the needed microstructures to achieve its function. So what I want to say is that while I find my research and also the education I do at MIT extremely exciting and motivating for me, and it has been really an incredible career to have. It's sort of like the dream job that you can't imagine that you actually lucked into being the one to get to have this job. The other huge way that you have your impact is not just through this research and the education, but all the people you touch. We're going to hear from Barbara and Caitlyn about some of our other programs at MIT directed towards our high school students and also towards our undergraduates. But I also want to just point out here is that when you're in your research, you really have a huge opportunity in one-on-one mentoring with your graduate students, with your postdocs. And these students also then go off and mentor another generation of students. And you never, you find the number of people you actually end up touching, whether directly or indirectly, is really a rather amazing aspect of your career. And it's something I remind my faculty about every day, is that our impact is as much through the people who come from our groups, from our classes, as it is through the actual research that we're doing. So here, I just thought there was kind of an interesting thing. I was thinking about this yesterday, of just when I think I have had 26 PhD students, 10 of them have been women. That's actually rather unusual in engineering to have that kind of a ratio. And many of the women have gone on to academic careers. So I've just decided, let me see where they are. And so I put a star on some of the locations in the U.S. where of women, and this is just the women who've done a PhD with me, who are an academic, or a faculty member. One in New Hampshire, one up at Harvard, one at Johns Hopkins, one at Cornell, one at Ohio State, one at Northwestern, one at University of Michigan, one at Georgia Tech, and they've each obviously gone on and had their own impact, quite independent from me. And in addition, you actually reach across the world with this kind of a career. That, I have a student off in Korea. This is the big stars, all the ones I just showed you in the U.S. I have a couple of former students off in France, one in Turkey. So the impact you have, we think a lot about our papers, our research, and then our impact on how what we do enters industry and starts new companies. But it's also the people are like a tentacle that goes on and really is what continues to push that next generation. And I think we're going to really hear a lot more about that from Barbara Huey. So, and if you want to see hierarchical suture joints, please come up and I'll show you some of these. Okay.
Thank you, Dr. Boyce. You've just demonstrated that one of the things about a great teacher and mentor is that you always leave your audience wanting more. And I certainly hope many of you will come up and look at these suture joints, but I want to know more about our own. Very interested in that one. So speaking of Dr. Boyce's and mentees, allow me to introduce our next speaker, who is Dr. Barbara Huey, who's the Women's Technology Program at MIT and also Associate Director and Instructor in the Department of Mechanical Engineering at MIT. In 2006, Dr. Huey created the Mechanical Engineering Curriculum track of WTP, which is an annual 4-week residential summer program that introduces high school girls to the basic principles and ideas of electrical engineering, computer science, or mechanical engineering in the summer after the 11th grade. Dr. Huey.
First of all, I'd like to thank the committee for inviting me to talk. I'll be primarily talking about WTP, the Women's Technology Program at MIT, but Jen asked me to give a little snapshot of my history, which is somewhat varied. So I actually, it turns out, started in mechanical engineering, even though my degree was in engineering physics at Princeton University. I then came to MIT for a PhD in experimental atomic physics with Dan Kleppner, and that was studying quantum electrodynamics of atoms in cavities, really not applicable to most of anything, but fascinating research. I always regretted once I left grad school I didn't need quantum mechanics anymore because I really enjoy quantum mechanics. But then after my PhD, I worked in industry for about 10 years in the Boston area with several small companies. We mostly focused on applications of accelerator technology, primarily medical applications. I did a lot of work on developing accelerators, targets, and chemistry systems for positron emission tomography, and then also developing a sensitive carbon-14 detector, which is useful in drug development studies. And that company, Newton Scientific, actually still has 3 accelerators in use at MIT, 2 in the nuclear engineering department and 1 in the biological engineering department. And then about 10 years ago, I came back to MIT as an instructor. I'd always thought I would enjoy teaching, and this opportunity arose for me to come back and manage the labs for the junior level instrumentation and measurement class at MIT, working with Professor Ian Hunter, who had just taken over the class and was revamping it. And I've really enjoyed my time at MIT. Since I teach the junior level experimentation class, it's a required class, so I get to know all the undergraduate majors. And I teach them how to do experiments, and in fact, they have a long, semester-long self-directed project that we call Go Forth and Measure, where they decide what they want to measure and then measure it. Actually, Caitlyn did a fascinating study of cake baking in various types of ovens. We always have a lot of sports topics, people looking at the effectiveness of different sports. We had a fascinating one last year about looking at high-heeled shoes and sort of a pain threshold as to how high your shoes are. So it's always a wide variety of topics, so even though I no longer do any research of my own, I'm heavily involved each semester in about 70 to 80 independent little research projects by the undergraduates, which is fascinating. But I'm actually going to focus my talk on the Women's Technology Program. This is a program that, as was stated, is used to introduce girls in the summer after 11th grade to engineering. And our mission is to spark high school girls' interest in the future study of engineering and computer science. So the program approach is to admit students who are really good in math and science but don't already know that they want to be engineers. So these are students who haven't had much exposure to engineering, and but they're good in math and science, and we want to catch them right before they're going to apply to college and say, hey, engineering is a really fascinating major, you should consider it. We give them an in-depth 4-week exposure to engineering in one of 2 curriculum tracks. There's a track in electrical engineering and computer science, and then the track that I run is in mechanical engineering. So a little bit about the history. It was founded in 2002 by actually a male master's student in the Department of EECS who looked around him and said, there aren't enough females in this department. What can we do to improve that? And it's been directed since 2003 by Cynthia Skier, who's here, who's the director of WTP, who's done an amazing job. This program would not exist without her. And then, as was mentioned, we started the mechanical engineering curriculum track in 2006. This was partly an initiative by then Dean of the School of Engineering, Tom Magnanti, who saw how great a program WTP was and wanted to expand it to cover more departments. And mechanical engineering had a similar problem to electrical engineering and computer science in the dearth of female students, particularly at the graduate level. The undergraduate level, I believe, we're now 30-some%. But at the graduate level, it rapidly drops off, especially at the PhD level. So the philosophy of the program is to generate interest in engineering. We do that by doing a lot of hands-on classes and team-based projects. And we expose them to a broad range of engineering topics. Engineering is incredibly broad, something most of these students don't realize. For mechanical engineering, we ask them before they come what they think mechanical engineers do, and we get answers like building bridges and automobiles. But mechanical engineering, especially at MIT, is amazingly broad. When I first joined the department 10 years ago, I felt like it was like physics was at the beginning of the 1900s. So at the beginning of the 1900s, physicists did everything. I'm a physicist by training, so. But physicists did the theory, they built the instruments, they did the measurements, and mechanical engineering at MIT and also electrical engineering and computer science has expanded out into biology, has expanded into microfluidics, has expanded into so many fields that with mechanical or electrical engineering and computer science, you can do almost anything. So we expose them to that. The pointer that works is here. Let's see. There we go. So you may recognize this student. That's Caitlyn Rita, who you're going to hear from. That's her as a high school student. And actually, the student she's working with also was an undergraduate at MIT. And this is a quote from another student that said that she realized that engineering had so much more depth and so many more applications than she had thought. And she was looking forward to finding a specific field of engineering that really interested her and pursuing it in the future. Another big part of the program experience is not just the technical and academic part, but also to increase the students' confidence, to expose them to female engineers of all ages, to give them good role models, and let them experience living away from home on a college campus. Some of the students have done other summer programs before, but for many this is their first experience away from home. So to live in a dorm for 4 weeks is very interesting. And they also have to learn how to work in teams. And they discover that we throw very complicated topics at them, basically going up towards college level, and they discover that they can actually understand them and be successful in this program. And another quote where a student said she realized that with cooperative support from the staff, she could learn anything, even without former background. So the way that we've structured the program is that it's a 4-week program. It's residential, which means the students live in dorms at MIT. We admit 40 students into the electrical engineering and computer science track and 20 students into the mechanical engineering track. We have hands-on lab classes with projects. We try to do a lot of hands-on work. As the Museum of Science knows, that's the way that people learn, is by doing hands-on work. So we try not to have a lot of lectures, but instead more hands-on activities. And then we have special projects in the last week, in the 4th week, which for electrical engineering and computer science is building a DC motor, which sums up a lot of electrical engineering. And for the mechanical engineering students, it's building a Rube Goldberg machine, which hopefully you all know that's basically a chain reaction machine. We put a twist on it in mechanical engineering over what some students do perhaps in middle school, is that we tell them they have to calculate or estimate what's going on in every step. So for every step, they have a step calculation sheet, and they have to describe the physics of what's going on. We have female MIT students or recent graduates who teach the classes and also who work as residential tutors. And so they help the students with their homework and also live with them in the dorms. And then we have a lot of faculty and industry guest speakers and also tours. So these are some photographs from the motor building, done by the electrical engineering and computer science students. So you see they get a chance to do a lot of hands-on work using tools. Here's the finished product right here. And we have a spin-off at the end. This is Professor Steve Lieb, who helps run that part of the program. We have a spin-off at the end to see who has the fastest motor. And here are some photographs from one of the Rube Goldberg contests. We give them a kit of assorted materials, including, of course, dominoes and funnels and balls and water, and they get to decide their final step. So this was a group one year that their final step was pulling a curtain which would unveil a photograph of all the WTP students. And I have a little bit of a movie. I can't show much of it due to time constraints, but this was from the summer of 2011, which, if you recall, was when the last Harry Potter movie came out. So we have a bit of a Harry Potter theme here. These were the Slytherin girls, so. So they all make a cartoon of their drawings, similar to those that Rube Goldberg would have made. And then this is just sort of showing you the layout and some of the materials that they used. You may recognize a Newton's cradle there, the momentum transfer object, which you probably have all seen. And this one, the final step was pouring a martini for me. It was, of course, water, but. And we do this contest in Lobby 13 at MIT and get a nice crowd. I'll show you one more and then I'll move on. And they have to use elements from the topics we've taught them, such as fluid mechanics, structures, materials, you know, all the basic mechanical engineering topics. And they're also required to have their machine run for at least 30 seconds, which means that many of them have a slow step. That last one was a relatively quick machine. This one, you'll see the slower step. So here's the slow step, which was melting ice, I believe. We won't sit and watch the whole thing. And their final step was to cut a banana. So in terms of the impact and the success, we survey the alumni after they leave the program. We've also surveyed them before so we can compare their answers before and after. And we found that most of them affirmed that it had a huge impact on them, that before they attend WTP, they probably would not have applied to an engineering college. They probably would not consider applying to MIT. And they probably would not have majored in engineering or computer science. However, after the program, the statistics we have, this is for the students through the WTP class of 2011. We have a little over 500 alumni. And of those, we know about 360 of them, we know their majors because the others are freshmen or sophomores, and so they haven't declared a major yet. More than 60% are majoring in engineering, which is, I think, really great. Thank you. Some other statistics, we do not have a goal of getting students into MIT, but of course, once you've been at MIT and you see the incredibly invigorating atmosphere, they all want to come to MIT. So we end up about almost 40% of the alumni have or are attending MIT as undergraduates. And of those, 76% with declared majors are majoring in engineering. And it's almost 30% in EECS and a little over 20% in mechanical engineering. So I would say our numbers both on the whole and at MIT are incredibly encouraging. And, yep, there we go. I don't know that I have time to read these, but basically we have some amazing testimonials from students that say that when they came to WTP, you know, they had no idea what engineering was, they didn't know what engineers did, and they discovered a huge amount of things that they could do. And they also love the learning environment because this is often their first experience with real team learning. In high school, it tends to be more do your own work and don't cheat by working with other people, whereas in engineering and at MIT, it's work with other people, collaborate with other people, you can learn from them. So we make a big point of that. And this is actually last year's class, so you have 60 students and then all the staff spread around in the different colored t-shirts in the back. If you'd like more information, our website is easy to remember. It's wtp.mit.edu. And if you know students who are girls who are in the 11th grade and love math and science and don't know much about engineering, please point them in our direction. Our application deadline will be, I think, January 1st. And so some acknowledgement. So first of all, Cynthia Skier, this program absolutely would not exist without her, so I would just like to thank her. And then I personally have to thank Britt Darbeloff, who, first of all, I think was instrumental in getting me invited to talk about the program and also has been supporting the mechanical engineering track of WTP since our second year, and I have to thank her so much for her help in that. And then finally, all the deans and department chairs. The Center for Material Science and Engineering at MIT is instrumental in the DC Motor Building, and then this program wouldn't exist without all the staff and also the former students. Thank you very much.
Thank you, Dr. Huey. That was really fabulous. And it's really, I think, inspiring, and the program seems absolutely wonderful. And now I think we want to hear from a very special person who's a WTP success story, Caitlyn Rita. Caitlyn is an alumna of the inaugural Women's Technology Program in Mechanical Engineering and a two-time residential tutor for the program. She's now a graduate student in Mechanical Engineering at MIT. Caitlyn.
Hi, everyone. So first of all, I'm honored to be here. And I guess I'm here as both a mentor and a mentee. So first, I'm going to start with a brief history about how I became a woman in engineering, and then I'm going to go over a brief overview of my current research. And then I'm going to talk about my experience both in WTP as a student and as a staff member, and how mentorship has played a role in my life. So I grew up in the Silicon Valley with two software engineers as parents, and so I was lucky to kind of be surrounded by engineering in the early stages of my life. Except my first real hands-on experience with engineering was actually in high school through the FIRST robotics program. And if you haven't heard of the FIRST robotics program, it's a really good program to get kids of all ages into science and technology. However, it wasn't until the summer after my junior year of high school, when I attended WTP, that I finally realized what mechanical engineering meant. And I realized that everything that I loved about robotics was in mechanical engineering. And in 2007, I was accepted into MIT, and I went there for undergrad. The following summer, I worked for WTP again as a residential tutor. And in 2011, I graduated with a mechanical engineering degree, and that same summer, I worked again for WTP as a residential tutor. And in the fall, I came back to MIT to start my graduate program. And so I guess now I'm in my second year at MIT, and I'm in a master's program with Professor Hart in the Laboratory for Manufacturing Productivity. And we're working on manufacturing microfluidic chips. And so microfluidics, they basically use small-scale features to run laboratory tests. So for example, if you have a drop of blood, you can check if someone is positive for malaria or if they're HIV positive. Or you can do other tests such as cell sorting or PCR. And so because such a small amount of reagent is used in these microfluidic chips, they're very low cost. It's very easy to take these chips and bring them out to the field, so you can bring them places like third world countries where you don't have access to these labs. And so what we're trying to do is build a desktop factory that can manufacture these chips more cost effectively. And we're trying to do this by using hot embossing. So here is the factory that we're building. And here is an example of the hot embossing process, which basically takes it takes a tool and heats it up, and takes a substrate, heats that up, and then presses them together like a hot stamp. And after that, we put a layer of adhesive tape over them to seal them, and then we test them optically and functionally. And with that information, we can feed the information back to the hot embosser and run cycle-to-cycle feedback control so we can get that micron scale precision. So I definitely have WTP to thank for leading me in the mechanical engineering direction. I definitely wouldn't be here without it. I absolutely loved the hands-on activities that we did. Dr. Huey briefly mentioned some of them, but I wanted to give you a better idea of all the cool things you do. So for example, we would strap accelerometers and heart rate motion sensors to ourselves and ride roller coasters at theme parks. We visited tons of labs, both on and off campus. Here we were at the Otis elevator testing facility. I also had a blast in building the Rube Goldberg machines that you guys saw earlier. And also I found out that I must have been a relatively obedient kid when I was little because I never took things apart. But when I came to WTP, they gave me a kit and they gave us a stack of old printers and told us to take them apart and figure out how they worked. And so that is what we ended up with. And as Dr. Huey mentioned, WTP is a whirlwind introduction to all sorts of core engineering topics that you learn as an undergrad in mechanical engineering. So there's the statics, dynamics, fluids, thermo, there's design, MATLAB, and SolidWorks. And I remember when I was in WTP, I was having so much fun with SolidWorks that I was staying up really late trying to perfect a little CAD model of a whiteout tape dispenser that was in my backpack. And I just had so much fun with this. And another thing they do is that we do was one of the undergrad level projects. It's an experimental a lab that you do as an undergrad at MIT. But you get to do that as a high schooler and actually understand all that's going on. Oh, and also I wanted to mention how we would have these great lunch seminar talks from all sorts of people, professors, grad students, everyone about their research. And by having them come and talk to us, we're finally able to realize the extent of mechanical engineering and in how many ways it could be applied. And I think that made me understand, because before, I thought mechanical engineering was only for people working on cars. Like, I really had no idea what mechanical engineering was. But afterwards, I realized that mechanical engineering is everywhere. Like, you could find something in anything that you can use it for. So when I came back to WTP as a staff member, I realized I was having just as much fun because you're reliving all the same experiences. You're seeing the same excitement in every new student that comes. And when I came back, there were a couple new additions it's evolving over the years, it's getting better. We started taking apart things like vacuum cleaners, CD players, furry mechanical ducts, just everything. And another one that I really like is that the students get to design and simulate an airfoil. And then once they finish simulating it, they get to build it and then test it in the MIT wind tunnel, which just seems like a great experience. And I finally want to mention two specific girls that I mentored that I thought that really made this experience worthwhile for me. This was Ingrid and Schwen. We're working on their final poster project, and the goal of this project was to build a structure out of balsa wood and floss, and it was supposed to be able to support 50 pounds. And it also had to be able to fit over a certain area, so it couldn't be supported from underneath. And so these two girls used what they learned in statics to build trusses and I-beams, and they were just having a blast making it. It ended up holding 50 pounds. It ended up holding one of them. They were able to sit on it. And as you can see in the bottom pictures, it didn't hold both of them. But I just thought this was such a good example of how I felt as a mentor and how this was so rewarding for me, because these two girls were clearly having a great time. Even outside the project, they kept coming over to me and being like, "Hey, Caitlyn, look at that. It's a truss structure on the bridge." Or like, "Hey, Caitlyn, it's another truss structure on the ceiling," or something. And I just felt so good because it reminded me also of how I felt when I was first in WTP and trying to figure out what mechanical engineering meant. And so I think it's really important to have this mentoring cycle going on, not only to help girls, but also to help yourself remember what it's like and where you came from as a mechanical engineer. So thank you.